Good afternoon, everyone. My name is Rajat Bonik. I am from IITISM Dhanbad. I am one of the PMRF research scholar at IITISM Dhanbad, and I am one of the teaching assistant of this course, Nptel course, Foundation Engineering, which is conducted by Professor Dilip Kumar Vaidya sir. And I have also 6 months experience, teaching experience in NPTEL uh, on the course of ground improvement, which also conducted by Professor Dilip Kumar Vaidya sir. So, in this today is week 4 of this foundation engineering class, a problem solving class. So, we start our session very soon. So, I like to uh, conclude. I like to give some important information to you that these lectures are recorded and it will be uploaded on my YouTube channel. You can access through by NPTEL, and whatever I am discussing today, all the lectures material I upload it on my Google Drive, so you can access it. And in this today's session, one more thing, that if there is a problem of network disconnection of network or any problem regarding the network issue, if my line may be cut due to some network issue, so don't worry, please stay on the line. I will solve it very quickly, and again I will join the meeting. And during my session, I will also give a 5 minutes break at the midpoint of our session. That means after 1 hour, and we start this, and then we continue our session again. And in this session, I first go through the uh, week 4 lectures. 5 lectures are there in very shortly, and I very quickly I am go through this, which is taught by Professor Dilip Vaidya sir, and then we solve some problems on this week regarding this week's class problem, and also the previous year assignment problems 2020 and 2023. I think this is enough to uh, for this week 4, and now I am start my today's session. So I am sharing my screen. Please stay on the line. I think it is visible to everyone. I think it is visible to everyone. Please stay on the line. Uh, Now I think my skin is visible to everyone, and my voice also clear. Hello. Okay. So I now start our session from lecture 16 in week 4. So in lecture 16, actually it is the recap of all the lectures, foundation engineering. Whatever we go through this week up to week 3, we very gist. we very quickly discuss in lecture 16. Actually, it is the gist of week up to week 3. So now we very quickly go through it. So in lecture 16, this it is discussed about the mat foundation. First, it is discussed about the mat foundation. Mat foundation is nothing but a like a slab of our building, but this slab is constructed on the ground surface. So if you see our roof of our RCC building is a flat surface up to some thickness. So like this way we construct our foundation, mat foundation on the ground surface is to on which all the columns are situated and transfer the load of the structure up to a large extent over a large area on the ground. So it is said that a mat foundation is used when the subsoil is very weak. So we generally use when the subsoil is very weak and the column loads are so heavy that the conventional spread footing cover more than 50% of the building area. So column loads also very heavy. That means soil is very weak and structural load also very high. Then we use mat foundation, and another condition also there. If the 50% of the spread footing, if the more than area of the spread footing is more than 50% of the building area, then it is better to construct mat foundation. And on the mat foundation, all the columns are constructed. So there is no gap in between this. So then a mat is preferred to individual footing when the soil mass is very erratic and contain pockets and lances of compressible soil. So it is said that the mat foundation when the soil is very erratic, we use mat foundation. That means there is some good soil, there is some weak soil, again there is some good soil, there is some weak. So we don't know what happened uh, next to our soil condition next to our soil. Also, the changes of strength of the soil is very erratic, means very changing regularly. So then we use this mat foundation. Again there is contain some pockets. Pockets mean void. You see that some below the ground surface there is a hard layer. Below the hard layer there is some voids present. Due to the earthquake, this void get loosen up and the structure may fall due to the uneven settlement of the ground. Then there is presence of lenses. Lenses mean in between two hard layer there is a one uh, compressible layer. So if we apply the load over the hard layer, the ground may be compressed. So due to this, the structure may fall. So for this, we use mat foundation. To overcome this situation, we use mat foundation. So then, in such a case, individual spread footing are subject to large differential settlement, whereas the mat bridge over the patches of weak soil and the differential settlement are considerably reduced. So, due to this condition, we know that differential settlement happen in spread footing. To overcome this, we use mat foundation. So there are different types of mat foundation are there. So first one is flat plate mat foundation. That means one plate type structure is built on the ground surface and over which columns are situated. Then flat face thickened under column. That means under the column the plate thickness is increased, but away the column the plate thickness are reduced. Then uh, mat foundation as a beam and slab. That means if you see that our roof is contain some beam, and over this beam the we construct our slab. Like this way, we also construct our uh, mat foundation in our roof structure. Over there is a beam we see, which is connecting to the columns like this way, and over this beam we construct our slab. Uh, so these are the section and these are plan view. Then again there is another type of another types of mat foundation, that are flat base with pedestal. Pedestal means in it is similar to flat plate thickened under column. So in thickened under column we thicken the plate below the ground surface. But in case flat plate with pedestal, we thicken and the column above the ground surface, above the flat plate. So this is called flat plates with pedestal. Then slab with basement wall. So see that, you also see that in malls and shopping malls, there is basement. So we actually the basement is built on the mat foundation. So about this we constructed column like this way, one story building we constructed. So like this way, we construct the bent foundation like slab with basement wall. Now we recap or summarize our uh, lectures up to week 3 here. In week 1 to 3, we studied about the different types of shallow foundation, what is foundation, and what are the factor governing this foundation or size of the foundation. Then we discuss about the types of the shallow foundation and how we differentiate the shallow and deep foundation. And we also found out the formula of find out the bearing capacity of the foundation. Bearing capacity, actually the load carrying capacity of the soil, we call bearing capacity. And this for bearing capacity for safe bearing, then we found out safe bearing capacity, which is safe from shear failure. And we also found out the allowable bearing capacity, which is safe from shear failure, also the settlement failure. So here some formula is given. That means we found ultimate bearing capacity to find out. That means ultimate pressure that one soil can resist below the foundation. Then we found out the net ultimate pressure by subtracting the surcharge over the foundation. Then net safe bearing pressure by dividing the factor of safety. We use factor of safety to reduce the uncertainty of the soil condition. We know that soil at the present moment sometimes soil is reacting very good way, but due to some earthquake issue or some seepage or above rising of the groundwater table, the bearing pressure may be or strength of the soil may be get reduced. To overcome this, we use sometimes overcome these uncertainties to use factor of safety. So, and this if you apply factor of safety on the net ultimate pressure, we then this is called net safe pressure. Then after getting the net safe pressure, if you add the surcharge, then this is called the safe bearing capacity. And if find out the Tarjagi given the ultimate bearing capacity for the seafloor soil on general shear failure condition, it is for stiff footing, it is the CNC plus QNQ plus half gamma B N gamma. Then shallow foundation. For square footing, this formula gets modified. We use 1.3. Also here we use zero point 0.4, and everything is same. And for circular footing, it is same 1.3 as like a square footing, but in uh, circular footing, this is zero point 0.3. So these are NC, NQ, N gamma bearing capacity factor. C is the cohesion, Q is the structure, B is the width of the foundation, and gamma is the unit of the soil. Then for stiff footing and phi is equal to 0, then our n gamma is 0, for phi is equal to 0, and c is 7.5.7, and q is 1, and it is given by Tarjagi. Remember it. For ultimate bearing capacity of the resting on the cohesive soil or net ultimate bearing capacity, it is become 1.7 C. Or resting on the cohesive soil, that means gamma df is equal to 0, then it is become on 5.7 C. For square footing, it will circular footing, it will be 1.3, 5.7 C. For shallow foundation at embedded footing in cohesive soil, we add above formula, we add gamma df in each of the case. Then ultimate bearing capacity resting on the cohesionless soil where C is equal to 0 and Q is equal to 0. That means such as 0, then formula become half gamma B gamma for sheet footing, zero point 0.4 gamma B and gamma for square footing, and zero point 0.3 gamma B and gamma for circular footing. So you should remember all of this, or either you remember this condition and general formula and apply this condition, and we get this formula. So this formula is very important for solving the MCQs. Sometimes the examiners set the question, direct question based on this formulas. So you should be very careful. Then in the foundation, we also consider the effective water table. We know that if the water table, that means ground water table is rise, then or very close to the foundation or above the foundation, then the bearing capacity may get affected and it reduce the bearing capacity. So when the water table is greater depth, greater than the width of the foundation from the base of the footing, then the formula may not hamper. But it is the water table at the base of the footing when the condition is the cohesionless soil resting on the footing is in the ground surface, then the formula is half gamma dash B and gamma, and how gamma dash is the submerged unit weight, and it is become gamma saturated minus gamma W. All this formula we discuss in our up week 1, week 2, week 3 accordingly. So you go through it once. Then we come to Mayer's theory, and which is governed by the shape, depth, and inclination factor of the load. The shape of the foundation, depth of the foundation, and inclination of the loading. It is governed by, and there is some factors are taken care. All of this, that is SC, SD, ST, DC, IC, SQ, DQ, IQ, S gamma, D gamma, I gamma, and this formula is without the effect of water table, and this we in this formula we don't consider the effect of water table, and it is given by Mayerov, and it is most widely used, and it give almost exact result because it considers the all of the factors shape, depth, the foundation, and inclination of the loading. Then we go through the effective area method. Due to the eccentricity, we know that due to eccentricity, the effective area may get reduced if the eccentricity, if the load acting on the footing is not go through, is not coincide with the CG of the footing or at the center of the footing. So there may be the effective area of our foundation is reduced. This is reduced, and we get new effective area that is become B dash. That is not point. So the B dash is B minus 2 into eccentricity, and our new area is L into B dash. If we consider the eccentricity is along the width of the foundation. So you see that. Then we also find out the maximum pressure generated below the foundation, or we can say stress below the foundation due to direct stress and due to the bending stress. So if the one-way eccentricity is present, our minimum and maximum pressure below the foundation is, that means, is P by L B. L is the length, P is the width, and P is the pressure or load coming from the column structure through the column into 1 plus minus 6 E by B. E is the eccentricity, B is the width of the foundation. If the two eccentricity, then our maximum minimum one extra term is added, that is 6 ex by L, and here it is, and all the, for minimum we use negative sign, for maximum we use positive sign. Now in week 17, week 4, lecture 17, we uh, discuss about the settlement of the foundation, mostly for the settlement of the shallow foundation. And actually, in bearing capacity formula, we find out the safe bearing capacity. Our ultimate goal is to find out the safe bearing capacity. But the safe bearing capacity is safe from the failure of shear. But our structure may also get failed by the settlement of the foundation due to the pressure coming from the structure, and this pressure may reduce the volume of the soil, and structure uh, may get fails due to the uneven nature of the settlement or uneven nature of the movement of the foundation. Cracks develop, stress develop, and structure may get failed or tilted. So now we discuss the settlement of the foundation, mostly for shallow foundation. And this settlement is divided in three types. One is immediate settlement, then primary consolidation settlement, and secondary consolidation settlement. This this immediate settlement is based on the elastic, is also called elastic settlement, which is follow the elastic theory. And this primary and secondary consolidation settlement is based on the plastic theory, and it is plastic failure. It's like plastic failure, and it is occur when the structure, we see that if below the foundation the pressure may vary like this, and immediately means at the time of the construction of foundation, there may foundation soil may get settled immediately after constructing the foundation, and this pressure is lie in between the elastic zone, and this settlement is called elastic settlement. After the period of time, some time the pressure is increases gradually, and soil may get fail because soil is a uh, non-linear in nature. So there is no straight line regularly like this. The pressure distribution like this way. After some elastic point, there is a plastic failure occur. That means stress is same, but settlement is continuous go on, or pressure load is same, the settlement is continuous go on. This failure is called plastic failure, and this due to this plastic failure, the settlement occur is called primary or secondary settlement, consolidation settlement. And mostly this settlement is consolidation settlement. So in sand, this so in most of the cases, the primary and secondary settlements occur in clay soil, and immediate settlements occur most of the case in sandy soil. That means percentage of immediate settlement is high in sandy soil because consolidation settlement is occur only in clay soil due to the less permeability of the soil. So you see that there is one table given in sand, the percentage of settlement, total settlement due to the immediate settlement is about 70 to 90% for sand. Stiff clay it is about 40 to 60%, and soft clay it is very less. That means 10 to 25%. Here is the time versus settlement curve. So you see that this is immediate settlement occur at immediately after the construction of the foundation, and then there is occur primary settlement at a time of t, it is up for consolidation, and then there is secondary settlement due to the sinkage or like other factors. Now find out the immediate settlement. For finding out the immediate settlement, we use the elastic theory, and it is here we are using it that strain is, we know that three-dimension strain is that if you stress one block in three directions, then there is strain generated and one direction is depend on all the three directions. So here we formula it is epsilon z is equal to sigma z by E minus mu by E r plus sigma r plus sigma t. If you integrate this epsilon z with respect to dz from 0 to infinity, that means here it is 0 and semi infinity zone it is infinity, our depth is infinity, then we get our total immediate settlement, and it is become uh, QB by E into 1 minus mu square into I. I is the influence factor. It is mostly depend of the size of the shape of the foundation. Use the pressure coming from the structure. B is the width of the foundation, is the elastic modulus of the soil, mu is the Poisson's ratio of the soil, and that is if I is the influence factor, and it is depend of the shape and types of the footing. Then this value of I for rigid footing, that means the foot foundation is very rigid, it cannot be bended, and if we apply load, it is go or settlement is uniform. This is called rigid footing. High rigidity, that means modulus of elasticity, sorry, rigidity modulus is very high. That means EI of the foundation is very high, about infinity. Stiffness of the foundation, that is K, is very high. It is about infinity. So for different types of foundation, and the value is different, and you go through this table for rigid footing. Similarly, for flexible footing, that means the foundation apply when we apply load, the foundation may get bending occur in foundation, and the settlement of the foundation may not uniform under the uh, footing may not uniform. And for flexible footing also, it is depend on I value also depend on different types of uh, foundation. For circular it is about 1, maximum value is 1, and like this, and for square it is 1.12. We go through this table. Now settlement foundation, settlement of the footing resting on the soil of the finite depth or on a layered soil, which is given by Scrappman's method Scampton method. So in our above formula, which is we uh, found out based on the elastic theory, it is for infinite depth from 0 to infinity. Infinity. You see this formula, our settlement is from 0 to infinity. But in the pectoral case, there is some hard layer or hard stratum or the soil present below the foundation is in layer form, in different layer form. Then this formula is modified and it is given by Scammans, and this called method is called Scammans method. So he is given for different types of footing. One is given for stiff footing, another is given for square or circular footing. So in stiff footing, so below the foundation surface from here, the pressure distribution uh, of the foundation is like this. For stiff foot, and the length of this for stiff footing, pressure is up to that, and at some point the pressure is become zero. And we also call influence of the influence factor is become zero. And this length is from here to here, it is 4b, and at a depth b we get the maximum influence factor, which is equal to the zero point 0.5 plus 1 point into root over QEF by sigma dash b, where sigma dash b is the effective uh, effective earth pressure, or sorry, effective stress uh, at a depth of b, and QEF is the QF minus gamma dF, where QF is the pressure coming from the structure on the footing and gamma dF is the surcharge. So first we find out to this triangle to solve our problem. So before solving our problem, we construct this triangle and we divide in layers for different properties, due to for different properties. That means if we construct below our ground surface, our footing, I draw here, our footing is like that, and below this footing there is different layers like based on the Young modulus of the soil, E1, E2, E3, like this. So we also divide our this influence diagram according to our layer. Then first we find out this triangle. So this triangle is at, here is influence factor is 0, here is influence factor zero point 0.1, and the height of this uh, height of this shape is about 4b, and the maximum we get at a b if for stiff footing. You remember it is for stiff footing, and to find out this maximum we use this formula, influence factor, we use this formula. After that we find out, based on the similar triangle method, we find out the influence factor at the edge of the layer or at the boundary of the layer or different layer, like this, and we calculate the influence factor for this zone at the middle depth of this zone, like this way, and sum it up it or sum up using next slide we see here. By this formula we find out our total settlement, elastic settlement for finite depth, and these are the coefficients C1, C2. We find out based on this formula. QS is the surcharge pressure at the foundation level, that is gamma into dF. Then C2 is the depend on the time of construction. At what time, that means the time in year, and we this time is the uh, in at what time we need to require our find out our settlement. That means after construction of the uh, foundation, we need to find out the settlement after 50 years. After 50 years, what will be our settlement? So for this, we use this formula C2, uh, and this this time is governed by this factor, and this time is in year. So if we apply this formula, mainly this is for different layer. That means for different layer, I influence factor is different. For different layer, each thickness is also different, and for different layer, Young modulus also different. So based on this formula, we find out our elastic settlement. Then we also find out for this elastic settlement for finite depth and different layer. For square footing, there is some modification of this influence diagram. So in case 4B, it will become 2B for square footing, and the maximum influence factor below the foundation level. Remember, this diagram is drawn below the foundation level. So that is we and first square footing or rectangular footing. Sorry, for square and circular footing, this maximum we will get at a depth of v by 2 from the foundation level. And similar procedure apply to finding out the elastic settlement. So now we move on to lecture 18. There is one uh, problem based on this formula to find out the elastic settlement by using the Scantron influence factor, and they are given that at a different depth uh, the soil properties is changes based on the SPT number, and from the ground surface we see that there is three layer is given. So layer also divided, some specific points are given for dividing the layers. So due to this uh, one relation also given. One relations also given to find out is Young modulus of for different layer, which is nothing but equal to the SPT number in mn per meter square. That means mega Newton per meter square. Then unit of the soil also given. Pressure from the structure on the footing is given. Size of the footing also given, and type of the footing also given. Remember, the square footing. That means we're using second types of this Kempton method. Then depth of the foundation is given, and it is said that to find out the uh, settlement based on the Scampman's method, influence factor method, after uh, 6 months of the construction. So our T is 0.5 because T is in year in our formula. So our T is 0.5. Now I go to in solution page. So you see that uh, in in solution. So we see that based on this formula, if we find out the QEF, which is equal to the QF minus gamma DF. So QF is 300, which is given into given to in the question, and gamma is given 20, so it is 280 kilonewton per meter square. And then we find out the effective stress from the ground surface at a depth of b by 2, because our footing is square footing. So for square footing, the maximum, if you draw here our footing like this from the ground surface, surface is uh, about 1. So our footing is and we find out the effective stress at a depth of d plus b by 2. So our effective stress will be 35 kilonewton. After applying this formula, for finding out the maximum influence factor, we get the maximum influence factor value is about 0.7828. So now we divide or find out the now we divide this influence factor diagram according to our different uh, SPT number, and we find out that means this according to the SPT number, the influence factor divided in 3 layer, diagram is divided in 3 layer, and we find out the influence factor for at the middle of the each layer with the help of this diagram. So for each layer, first we find out the Young modulus and convert this Young modulus Mn per meter square to kilonewton per meter square by multiplying the 10 to the power 3. Then to find out the influence factor at the middle of this each layer, we use the interpolation method and also use the similar triangle method. So like this way we find out influence factor at the middle of each layer. Then after that we or we calculate the C1 C2 factors, and we directly put all these values on it, and we get this C1 C2. After that, we using the elastic settlement formula, uh, which is for finite depth, which is C1 C2 QUF summation of if influence factor of each layer into height of each layer, then divided by the Young modulus of each layer. Put all this value and we get our settlement, elastic settlement. For total elastic settlement is about 23 mm based on the Scampman's influence factor method. The answer is 23. Then, so our week 18 also completed. Now we come to week 19. So in week 19, I think we have to check. Yes. So in week 19, we now discuss about the primary settlement, consolidation settlement, which is also called consolidation settlement, which based on the consolidation theory. So first we discuss about the consolidation, and uh, here some discussion there. You go through it. It is nothing but how what is the difference between the immediate settlement and elastic settlement. So this considered, sorry, immediate settlement, or can say elastic settlement and in between primary consolidation settlement. So this consolidation settlement occur for saturated fine-grained soil only. That means when the soil is saturated, then only this consolidation settlement may take place. And here it is 1 or 2 points are given that in it said that a large wheel load rolling along a roadway resting on the clay will cause an immediate settlement, which is recoverable once the wheel is passed. Because we know that the immediate settlement is nothing but the elastic settlement, and based on the elastic theory, we know that if we apply some load up to elastic limit, and if the material get changed or shape get changed, it will back to its original shape after removing the load. But if the same load is applied permanently there will in addition be the consideration. That means if you continuously apply this load on an addition, same load, then it crossed our elastic limit, and after elastic limit plastic failure occur. That means nothing but the consideration settlement may take place. Here, to find out this consideration, we use the consideration apparatus. Similar field situation, it is find out in laboratory. Similar field settlement field condition is applied, and based on this dial gauge, we uh, record the deformation, apply load, and the settlement of this soil we noted down. Here, the stress results are shown in the graphical form. Then this consideration settlement is represented in a very popular manner by void ratio versus pressure curve, and it is very popular in nature, and it is called EP relationship. That means E means void ratio, P is the stress or pressure, and this curve is negative curve. That means it is increase if the increase pressure, the void ratio get reduced, and if we unloading this pressure, the curve is go back, and this is called compression recompression, like consolidation recomposition, and the slope of this line is called coefficient of compressibility. And if we apply volume, or for we use for volume of the soil, then this is called coefficient of volume compressibility, and by this formula we find out the coefficient of volume compressibility, where which is equal to the A into dP by 1 plus E1 1 into 1 by dP, where dP is the change in pressure, A is equal to the slope of the this curve, EP curve, it is coefficient of compressibility. A is nothing but coefficient of compressibility. Then so our alt and E1 is the initial void ratio, also called E naught. So our coefficient of volume compressibility is equal to mv is equal to the a slope of the EP curve divided by 1 plus E1, and unit is mm square per mn. That means inverse the pressure unit. If we apply pressure in kilonewton per meter square, our unit will be meter square per kilonewton. If we apply the pressure in meganewton per meter square, our MV unit will be meter square per meganewton. Then here's one statement is given. For most practical engineering problems, MV values can be calculated for a pressure increment of 10 kN per meter square. That means MV is calculated for change of pressure 100 kN per meter square. Del P is equal to or dP is equal to 100 kN per meter square. In excess of the pressure, a present overburden pressure at the same depth. So if there is present overburden pressure is P naught, we add dP to find out our uh, coefficient of volume compressibility. So I think we should take break now. After 5 minutes, I will again rejoin and continue our session, today's session. In the next session, next our today's session, after break, we discuss our remaining parts of these lectures. That means the lecture 19, some few parts of lecture 19, and to complete part of the lecture 20, and then we solve the assignment problems. So stay on the line. I will join. Uh, I'll join again after 5 minutes. So welcome again this foundation engineering class. This is week 4 and I am now uh, conclude this remaining parts of these lectures, and after that I will solve previous year assignment problems, which is similar to your uh, assignments, this year assignments, and you get uh, the idea how to solve this question. So we discuss about the coefficient of volume compressibility. So it is very useful, this coefficient of volume compressibility, because by this coefficient you actually find out we actually find out the consolidated settlement if we know the thickness of this layer where we find out the consolidation settlement and the change of pressure uh, after construction of the footing. So by this formula, that is mv into dp into h, we get our total settlement. Now we know that this EP and EP curve is non-linear, or we can see that it is not a straight line. So if we convert this into semi-logarithmic scale, that means if E will be same in normal scale, but we change the pressure in logarithm scale, then it will become straight line. And the slope of the straight line is called compression index, that is CC. And by these formulas, we get our change in void ratio very easily, because it will become a straight line and it is very easy to calculate now. So here the change in, or we can say change in void ratio, that is E1 minus E2 is equal to Cc, that is compression index, into log 10. Remember, we change this pressure based on the logarithm scale based on E10 base, that is base is 10. So log 10 into P1, that is previously present pressure, plus del P, that is change in pressure after the construction of the foundation, divided by previously present pressure of the ground surface. Then here it is given some curves, points, you go through it. Then now we know that consolidation is different uh, two, divided into two, that is normally consolidation and over consolidation. So the term normally consolidation is come with the normally consolidation clay, consolidated clay. So it is said that a normally consolidated clay is that one which has never experienced a consolidation pressure greater than the overburden pressure. That means if our pressure if we apply pressure is less than the overburden pressure, that means the pressure already present on the ground surface, or which is the pressure which is go through this ground surface, then this is called the normally consolidation pressure, the normally consolidated clay. So you see here some discussion are given. It is very simple. So from, but if our considered clay is the the clay is one which has our considered clay is the one which has been subjected to a pre-consolidated pressure in the excess of its existing overburden, and the resulting compression being much less than for a normally consolidated clay, and also call that the semi-log plot is no longer a straight line, and the compression index value for our considered clay is no longer constant. That means the slope is continuously changed due for our concentration clay. That means our concentration clay is that clay if the pressure or pre-existing overburden, the pressure or pre-considered pressure is excess of its existing overburden pressure. That means if we apply the pressure which is greater than its existing overburden pressure, then it is called the overconcentrated clay. And in overconcentrated clay, the compression is very less based from the less than the normally concentrated clay. And if we plot the semi-log curve previously, it will come straight line. But in case previously it is become straight line. You if you remember in the previous year it has become straight line. But in our concentrated clay it not become straight line. It is a non-linear type curve. So and for this the coefficient of compression index, that means slope of this uh, curve also get change. In previous case it is will become constant because it is straight line. Then we come to or move on to the lecture 20. So in lecture 20 we find out the settlement based on this compression index, or we apply this formula, which is nothing but if we in this we know that del H, the change in the settlement of a layer divided by the thickness of the layer is equal to the change in void ratio divided by 1 plus E1 or E naught. So if we replace the del E by our previously formula for compression index is del E is equal to the Cc into log 10 P1 plus del P divided by P1, then we get this formula. And if we multiply H in the right side, then we get this formula. And by this formula we easily find out the uh, settlement with the help of the compression index. If the compression index is not given directly, but the liquid limit of the soil or clay is given by using this formula, that is point 009 into uh, liquid limit minus 10, and liquid limit is in terms of percentage, then we easily get the compression index, and this formula is given by the Tarjagian peak in 1948, and this relation is given Tarjagi in 1948. But the P is the overburden pressure, or we can say effective pressure on the ground, which is at a depth where we find out the our settlement. Right? At a point where we find out the settlement from the ground surface is the pressure, normal pressure, or sometimes we call effective pressure. So, but the del P, which is come on this picture, is nothing but the pressure created due to the construction, extra pressure created due to the construction of the foundation. So there, due to the construction foundation, the foundation also takes some loads, and these loads are transferred to the soil through the columns and foundation system. And this extra pressure is is the main reason to cause the change of the thickness of the layer, which is nothing but the settlement. So to find out this del P, there are some elastic formulation also given, or there is some pre approximate method also given. So based on the elastic formula for rectangular footing or load distribution formula, that means this del P is the increase of the pressure at the middle of the clay due to the load applied through the footing. We find out by this big formula also. where m is a by z, n is the b by z. Z is the depth at which we find out our del p, and b is the width of the foundation, a is the length of the foundation. So by this big formula, q is the pressure on the footing which is coming from the structure. So by this big formula, we find out our del p, or either we use the load distribution method at a angle or at a ratio of 2 is to 1. If a depth is z, then our at a load dispersion method, we can say load dispersion methods at a 2 is to 1. We using this formula also, or approximation also, we find out our del p. So we see that if the foundation is rectangular and width is L into B, or 2B or 2L, then at a depth of Z, our foundation will become, if our load distribution dispersion is 2 is to 1, our foundation become 2B plus Z, or here 2L plus Z, width is 2B plus Z, due to 2 is to 1 dispersion, because it is like that. If you consider this, here it is Z by 2, here it is also Z by 2. You consider this, here it is Z by 2, here is also Z by 2. So the pressure at a depth of Z will become, we know that pressure is force by area. So at that depth, the area will be modified. Distribution area is modified. It become 2B plus Z into 2L plus Z. So by this formula also, we find out our uh, change in pressure due to the construction of the foundation. So it is for rectangular and square footing, but in case of straight footing, it will there is one terms may get cancelled, and it will become fz by 2b plus z, because in straight footing L is much more greater than b. Now here one formula is problem is given to find out the settlement of a normally consolidated clay layer. So our normally normal stress is, or normally concentrated stress is less than the our concentration stress PC, and our thickness of the layer is 10, and natural moisture content is given, that is 40, that is WL is given, sorry, W is given 40 point 40%, 45%, that is 0.45. Then clay height, clay unit weight is given, gamma is given, gravity, specific gravity that means G is given 2.7, and liquid limit is given, W is given 65%. Then foundation is subjected, the middle of the layer of the clay layer, to a vertical stress of increase of 15 kilonewton per second. Then del P also given 15 kilonewton per meter square. Determine the approximate value of the consolidation settlement of the foundation if the groundwater table is at the ground level. So first find out. So we using this formula, that is del H is equal to Cc into H, thickness of the layer, into log 10 into P plus del P into P divided by P. So here it is said that the groundwater table is at the ground surface. So find out the settlement at the middle of the layer. So if there is 10-meter height, so middle of the layer height is 5 meter. So we find out first the effective stress at a depth of 5 meter, that is gamma dash into 5, where gamma dash is equal to gamma saturated minus gamma W. You consider the gamma W is 9.81 and gamma saturated is given is 17. So easily find out the gamma dash, and then if we multiply the 5, we get the our the P, that is P dash or sigma Z dash, and del P is given 15 kilonewton. Then we have to find out also this formula contain divided by 1 plus E1. So you have to find out E1. So for E1 and it is fully saturated, so S is equal to 1. So using formula ES is equal to WG, S is equal to 1, E1 you have to find out, W is given 0.45 and G is given 27. So you easily find out the E1. Then we have to find out the CC. For CC we using the formula 0.009 WL minus 10, where WL given is 65. We put value and get this CC. After that, if you put all this value in this formula, that is, I am writing again here, that is del H, that is settlement, is equal to CC into H, thickness of the layer, 1 plus E1 into log 10 sigma z dash, or we can say P1 plus del P, that is 15 kilometer per meter square, divided by sigma z dash. So by this formula we find out our settlement at the middle of the layer, at middle of the layer. So the solution is given here. We go through it, and it will become 34 mm. It is come in meter and converted it 30 mm by multiplying 1000. See that, find out the effective stress at a middle depth. It is 10 by 2, it is 5. After that we also uh, find out the E1 by this using this formula, then find out CC and put all this value and get this result. Now there is condition. The two conditions are there. If our problem is belongs to normally consolidated clay, then there is no problem to find out our settlement using the previous formula. That is like this only. But if our stress is greater than our consolidation uh, pressure, or then that is P naught plus del P is greater than our consolidation pressure, then we using this formula, where here CAR is the recompression index. Recompression index means if we unloading this, the curve, if you remember in our consideration chapters, we go come about like this. We consolidate, uh, we consolidate our clay. The curve become like this after removing the pressure. There is back, regain its strength or regain its size some about. After again applying the pressure, the curve is like this. So this is called CC, and this coefficient called CR, recompression index. So if we, our P naught plus del P is less than the uh, or over consideration pressure, then Cc will become Cr. That means we're using recompression index. But if it is greater than Pc, then we divide our zone like this. So here it is recompression CCR, here it is Cc. So up to this, our pressure is this P naught plus del P. Up to this is PCR. So using, and here it is P naught. So up to this we using CR, that is recompression index. Here you are using, after greater than PCR you are using the compression index. So you see that pressure is P naught, previously present is P naught, but from here the increase is PC minus P naught. So we apply. After that, the pressure basis line is PCR, and PCR plus P naught plus del P minus PC is the extra pressure. So put all this value, and if you rearrange this formula, the formula become like this. By this formula directly we find out if our total pressure after construction is greater than our over consideration pressure. For this case, we using both recompression index and compression index. Now we go to our assignment problems. So up to this, the lectures are completed. Week lectures are completed. Now we try to solve our assignment problems. Previous year assignment problems. So I we try to solve here the 2020 assignments. So now we one by one try to solve these assignment questions. 2020 assignment question. So there is 10 questions. There are 10 questions. So one by one I now try to solve it. You just look into this, and in first question it is said, asked that Tarjagi's one-dimensional consideration theory assume that which is, we know that based on the Tarjagi, there is four options are given. Which one is correct? We have to identify. So we know that Tarjagi, based on the Tarjagi one-dimensional theory, we came across one plot which is nothing but EP. So EP curve is not linear, but our option is given. All the options are linear. So we find out first option is wrong. Then if we convert this EP in semi-log scale, that means pressure is into a logarithmic scale, then this curve is become linear. So the relationship E versus log 10 EP relationship is linear. So correct option is option B. Then in question number 2, it is asked that the slope of the EP versus log P curve for a soil mass gives, or what is it is called. So if you remember that in lecture 20, or I think in lecture 19 last part, we come across with this, that is, if EP by E versus P curve, this slope is called A, which is called coefficient of volume compressibility. Sorry, coefficient of compressibility. So this slope is called coefficient of compressibility. When we interact this with or divided this A by 1 plus E1 or E naught, this become coefficient of MV, coefficient of volume compressibility. But when we convert this curve into semi-logarithmic scale, that is, we apply log into the uh, pressure. That means we convert pressure into logarithmic scale and remain the E void ratio as it is, then this curve become straight line. Okay, so this slope is called CC, which is called coefficient of compression index, and this slope is become now this logarithmic scale is become if we two points are taken, which is called P1 P2, that means log 10 P1 log 10 P2, and this distance is then this become E1 minus E2, it is E1, it is E2 divided by log 10 P2 minus log 10 P1. So it will be become CC is become del P, change in void ratio, divided by log 10 P1 P2 by P1, where P2 is the P1 plus del P. So our correct option is option D, compression index. Now we now go to question number 3. So please look look into question number 3, and it is said that or asked that the immediate settlement can be computed from the expression based on what? Options are given: theory of plasticity, theory of elasticity, Tarjagi's analysis, and pressure distribution. So if you remember in our lecture 17, I think we derived this formula based on the elastic theory. So the immediate settlement we also call the elastic settlement. So our correct option is option B, because if we remove the load, then the soil again gained its original shape. So again it is go its original position. So this settlement is called elastic settlement, and most of the case the sandy soil, most of the case this settlement are occur, and the major portion of this settlement for sandy soil is nothing but the immediate settlement or elastic settlement. So our correct option is option B. Then question number 4. In question number 4, it is asked that for most cohesive soil, for most cohesive soil, the larger part of the total settlement contributes from the. So we know that the cohesive soil is failed by the plastic failure or occur plastic settlement, and sandy soil occur settlement occur for elastic settlement. So the plastic settlement we know the it is called preliminary settlement, or preliminary consideration, or called secondary settlement. But in a cohesive soil, the major portion of this total settlement is occur for primary or preliminary consideration settlement. So our correct option is the reason is the in consideration settlement the cohesive soil is impermeable in nature, so the settlement occur is consideration settlement only. So our correct option is option B. Now there is one problem is given. So in question number 5, it is said that or asked that the immediate settlement find out in centimeter of a concrete isolated footing. So concrete isolated footing, it means a foundation is rigid and foundation is square, and also type of the foundation is square footing and also rigid. Then the founded on a depth of 1 meter, that means DF is 1 meter with a pressure of intensity 200 kPa or kilonewton. The Q is given to 200 kPa. On a silty soil with the modulus of elasticity is given 9000 kPa, E is given, Poisson ratio is given 0.3 and IF is given 1.12. So if you remember immediate settlement, we know that delta is equal to QB divided by E S 1 minus mu S square into I, where mu S is the Poisson ratio, S is the Young modulus of the soil. So Q is given 200, B is given 1.5 meter, E is given 9000, mu is given 0.3, I is given 1.12. Put all this value, calculate it, and get the result. And the answer will be D 3.4. I also solved this question. You see that first one. Put all this value, and it will become it will come in meter. Multiply 100, and it will become into centimeter, and answer is 3.4 centimeter. Option D. Now I think this question is understandable to everyone. Now we will go to the question number 6. So in question number 6, it is said that a 4-meter thick layer of fill material of bulk density is given 20 kilonewton per meter cube is laid instantaneously on the top surface of the 10-meter thick clay layer. If the coefficient of volume compressibility MV is given and gamma saturated for a clay are given, is equal to 3.2 into 10 to the minus 4 meter square per kilonewton and 18 kilonewton per meter cube respectively. The consideration settlement in mm we have to find for clay layer due to the placing of the fill material. So MV is given, thickness of the layer is given. So if you remember that for consideration on formula is given MV into dP into uh, thickness of the layer H. So we use this formula. MV is given, H is given, but DP is not given. So the settlement, why this settlement is occur in clay layer, we have to understand first. Understand this first. Because of the uh, 4 meter thick layer fill material laid on this clear soil, then only the settlement is occur on the 10-meter thick clay layer. That means due to the 4 meter fill material laid on the 10-meter thick layer, the settlement is occur at the clay soil. Remember. So due to this fill material laid down, the pressure will generated on the clay layer, and this pressure is nothing but the uh, nothing but the weight, or we can say yes, weight of the uh, or we can say yes, weight of this uh, or pressure of this weight of this 4 meter thick fill material. And if you find out this weight, which is nothing but 4 into height into gamma into L into B. L into B is nothing but the area, cross section area of this field. And it is if we convert this weight into pressure, that is P, we can say also call change in pressure, del P is equal to W into A divided by A, and put W value H gamma into A and divided by A, which will become gamma into H. So this H is nothing but the thickness of this fill material. Gamma is nothing but the unit of this fill material. So it will be P del P is equal to the 4 into 20, which is equal to 80 kilonewton per meter square. So put all this value here, and that is delta is equal to, that is settlement is mv into dp into h. Here h is the thickness of the clay layer. Mv is given 3.2 into 10 to the power minus 4. Dp is given. You check the units. All the units are same. Should be same. Kilonewton, kilonewton, kilometer per meter cube, meter square per meter. That means it is okay. Into h is here it is 10, and dp is we find out is 80. Put all this value and we get the result is option A, 256. I also solve this question here. We see that I first find out the pressure dp, then put all this value here and get 256 mm. Remember, our answer will come in meter. After multiplying 1000, we convert it in millimeter. Now come to question number 7. So in question number 7, one is wait. So now in question number 7, it is said that an isolated footing of 4 meter by 2 meter, that is rectangular footing in plane, transmit a pressure 150 kN per meter square on a cohesive soil with the Young modulus is 6 into 10 to the power 4 kN per meter square, and mu is given zero point 0.5. Find out the immediate settlement in mm, and we consider it is rigid footing. So we know that q immediate settlement delta is equal to qb by es into 1 minus mu square into I. So we have to find out all these values are given, but we don't know the value of I influence factor. But one thing is given, this rectangular footing where L is 4 and B is 2. So L by B is equal to 2. For rigid footing, rectangular footing in rigid condition, and L by B is 2. If we go to the table in rectangular footing, if you remember this, and L by B is 2, we find out that our influence factor is 1.12. So from this table we get influence factor is 1.12. We have to remember this table for different types of footing and also for different types of L by B ratio. So our influence factor is 1.2. Put all this value and get the result in meter. After multiplying 1000, we get in mm. So I solve it here. We see that for rectangular footing, L by B ratio is 2, I is 1.12, and put all this below, it will come in meter at 4.2 into 10 to the minus 3 meter, and if you multiply in 1000, it will come at 4.2 mm. Now come to question number 8. It is said that a 4-meter thick layer of a normally consolidated clay has an average void ratio of 1.2 is given. Its compression index is given 0.5. Coefficient of consolidation is given 1 meter square per year. If the increase in vertical pressure due to the foundation load on the clay layer is equal to the existing effective overburden pressure, the change is in the thickness of the clay layer in mm is, we have to find out. So it is regarding the consolidation settlement. So we know that primary consolidation settlement del H is equal to Cc into H, thickness of the layer, 1 plus E1 or E naught into log 10 P1 plus del P divided by P1. So here it is said that the change in, the increase in vertical pressure due to the sorry, foundation load on the clay is equal to the existing overburden pressure. So del P is equal to the P1. So the ratio will become 2 by 1. This ratio. Then it is also said that uh, the average void ratio is given. E1 is given 1.2. CC is given 0.5. Thickness of the layer is given 4. So put all this value on this. The trick in this question is we have to find out the P1 plus del P by P1, and it is nothing but 2 by 1. Put all this value and get the result. The result will come in meter. After multiplying 1000, it will come in mm. So you see my solution. You put del sigma naught plus del sigma divided by del sigma is 2. So our answer is 2273 mm. So now we go to the question number 9. Also, our session is at the end. So we also in our end session. Timing also running out. So in question number 9, it is said that to find out the this to find out the volume compressibility coefficient of volume, that is MV. So MV and given sigma dash given sigma dash plus del sigma dash also given, void ratio given, then uh, change in initial void ratio given, final void ratio is given, and thickness of the clay specimen is given. To find out the coefficient of volume compressibility. If you remember that coefficient of volume compressibility is equal to the A by 1 plus E naught, where A is equal to the change in void ratio divided by change in pressure. So put A value here, which is change in void ratio divided by change in pressure into 1 plus E naught, initial void ratio, where change in void ratio is 1.3 minus 0.9 and initial void ratio is 1.3, and change in pressure is nothing but del sigma naught, which is equal to the 500 minus 350, which is equal to 150. Put all this value here and get the result MV, and it is coming meter square per kilonewton. I also solved here. You see that first find out A and then put MV is equal to use this formula. A is equal to, so MV is equal to A by E naught, and get about 11.6 into 10 minus 4 meter square per kilometer. Now the last question of our session, also the assignment question. In previous assignment, last question is, it is very critical problem. So please uh, concentrate here. So in this question, so it is said that a soft, normally considered clay layer. So our question is about normally considered clay. So there is no problem of over considered clay formula. And thickness of the clay layer is given 8 meter. Natural moisture content is given 35%, and unit of the clay is given, saturated unit is given 20 kilonewton per meter cube. Specific gravity G is given, and liquid limit is given 55. Foundation, so we have to find out increase of pressure is given 15 kilonewton per meter square. find out the considered settlement at the middle of the layer. And unit weight is given, water is given 10 kilonewton per meter square, 10 kilonewton per meter cube, and groundwater table at the ground surface. It is similar to the problem of lecture 20, if you remember. Similar if data is changed. So we use this formula, is this similar problem. So first we have to find out the void ratio, initial void ratio. We know that the honor table is at ground surface, so S is equal to 1. So if we put ES is equal to G into W, this formula, we put S is equal to 1, G is 2.7, and W is the moisture content is 0.35. Put all this value and get the initial void ratio E0. After that, if we find out the compression index Cc is equal using this formula 0.009 into WL minus 10. So WL is here 55. So put value and get this Cc. After all of this, we have also find out the effective stress at the middle of this clay layer. So thickness of the clay layer is 8. So the our effective stress is gamma dash into thickness of how at the middle layer. Thickness of the middle layer is h by 2. So gamma dash is gamma saturated minus gamma W, where gamma saturated is 20, gamma W is 10. Put value, all this value, H is 8, so it is will become 20 minus 10 divided into 8 by 2, and we get sigma dash. So put all this value in this formula, consolidation formula, primary consolidation formula based on compression index. I write here. Del H is equal to Cc into H divided by 1 plus E naught log 10 sigma dash plus del sigma divided by sigma dash. Where sigma dash we find out gamma dash into H by 2, and del sigma is given 15 kilonewton per meter square. H is 8, Cc we find out 0.009 into WL, liquid limit minus 10, and then E naught is find out, E is equal to G into W, moisture content and unit of the specific gravity of the soil. Put all this value and get the answer. I also solved here that Cc we find out, E is find out, then effective stress also find out. Put all this value and get answer is about 230 mm. So our correct answer option is option B. So now I stop here. Our time also completed. Meeting time also completed. It is 6:01. So we will meet again in our next session. That is week 5. So by in very quick few session we completed our week 4, and this lectures is recorded and it will share also to you in my YouTube channel through my through Nptel, and this materials whatever I am discussing here is uploaded on my Google Drive. Please go through it, and if you have any doubt you can ask me in the next class, and I will try to solve your doubts or address your doubts. And one thing, in our next class we go into week 5 lectures. So by this time I stop here. So please go through this problem and try to solve week 4 assignment problems by your own, and it will be better for your exam purpose and also knowledge purpose. I also share with you the assignment solution of 2023. You also look into it and try to solve by your own first, and then see the solution if you have any doubt of this question. So now I am stopping here. So best of luck. So good night. See you again in the next session. So stopping, I am stopping here. Thank you.